Okay, so I'm going to tell you all a little bit about a package that I've been working on for the last 10 years called SDDP.jl. If you want to learn more, you can go to SDDP.dev. Why I think I need to give this talk is a lot of people have been using SDDP.jl for a long time, but I've never actually given a talk about it at JuMP-dev or put one on YouTube, so this is kind of a chance to do that. By the end of this talk, I hope you have some knowledge of the New Zealand dairy industry, maybe a little bit of knowledge about the New Zealand electricity industry, and kind of no knowledge of the actual inner workings of the algorithm. That's me on the left, when maybe I was about 11, in the cow shed of my parents' dairy farm. You can kind of see in the background that there's a couple of cows with their head looking in. And farmers face a really difficult optimal control problem under uncertainty over time, which is kind of described by this diagram on the right. So each week or each day is a kind of a time step in the life of a farmer. And at the start of the time step or the day, they learn 3 new things. They get to know how much potential evapotranspiration there is. So this is a combination of sunlight and air temperature. They can see maybe how much rainfall they had either overnight or maybe as forecast for the coming day. And they get to see the milk price. And then each of these little kind of sub-assemblies within the model is a different sub-model. So there's a water model for the soil. So the square boxes are state variables. These are things that the farmer tracks over time. So one of them is the amount of moisture in the soil. When rainfall falls on the soil, the amount of moisture in the soil goes up. Some of it can evaporate. You can pay for irrigation to put more water into your soil. When water evapotranspirates from the soil through the plants and the grass, grass grows. So another state variable is how much pasture there is in the farm. Some of the pasture dies. You can feed it to your cows. You can harvest it and put it into storage in the form of silage or hay. And then you can feed some of that grass to your cows. Or really, you put the cows on the paddock and they choose how much grass to eat. The more feed you give to your cows, the more energy they intake. You can either feed them grass, you could feed them hay from the storage, or you could buy in supplementary feed, most commonly in New Zealand in the form of palm kernel. More energy into the cow means that they make more milk. There are actually 2 types of cows. You can have a cow that is milking or a cow that is not milking. When they have a baby at the start of each year, they start milking, and at some point during the year, you can stop milking the cow. So it goes from the milking cow box to the dry cow box. And they have like different amounts of energy that they require depending on whether the cow is milking or not milking. You make some milk. You can either put it in storage, or what really happens is that the company comes and picks up the milk and turns it into milk powder or butter or cheese. But there's a futures market for milk in New Zealand, so effectively this is the milk storage is your kind of unsold milk. And then you sell some milk and you earn some profit. That's the life of a farmer in a day. What they're really doing, but they kind of don't know about it, they're kind of just using intuition and experience, is they're solving an optimization problem where at the start of the day they get a new vector x, which is their state variables, the soil moisture, how much grass they had on the farm, how many cows they had, how much milk they hadn't sold. They've learnt some uncertain information, this omega that's come in. That was the rainfall, the soil, rainfall, the price, and the potential evapotranspiration. And they want to minimize their costs or maybe maximize their profit. Subject to constraints, they have to keep the cow alive. Maybe they can only have so much grass in their storage, like they've got some capacity of how much hay they can store. They take some decisions. The state changes, so maybe water has left the soil, so the amount of moisture in the soil goes down. They've put more feed into the hay storage, and they get an X prime that's going out. That's the start of the state for the next time period. And so these little square boxes with squiggles coming in is kind of the diagram in the top right. These boxes get chained together into a Markov chain. So we have, in a year, 52 weeks. So each of the columns is a week in the life of a farmer. And the milk price is actually, can be modeled as a Markov chain over time, where we have this kind of branching process where it starts off at $6, and then by the end of the year, maybe it's $4, $5, $6, or $7. The real model can be more complicated than that, but they can kind of model the price as a random walk over time. And at the end of the year, there's some infinite horizon behavior where the farmer leaves the end of the year and comes back to week one of the next year. So they want to leave their farm set up at the end of the year to be in a good condition for the next year. And then kind of, if you were to solve this problem and kind of simulate years in the life of a farmer, walking through different prices and different series of inflows of rainfall and evapotranspiration, you kind of get some distributions of their states and actions over time. And you can kind of visualize the policies of a farmer, but we won't maybe go into the details. It turns out that the New Zealand dairy industry is very similar to the New Zealand energy industry. And paddocks are like lakes of grass, and when rain falls onto a paddock of grass, the lake of grass increases. In the energy industry, we actually have hydro reservoirs where rain falls into the reservoir and the water in the reservoir increases. You can then take water from the reservoir and run it through a hydro turbine, make electricity, and the water flows downstream into the next reservoir. That's kind of like taking grass from a paddock, flowing it downstream in the form of energy into the cow, where the fat in the cow increases. And then milk comes out instead of electricity. There's a futures market for electricity, there's a futures market for milk. Capacity expansion in the dairy industry is how much cows you put on your farm. And unit commitment is this decision to turn cows from milking to not milking. So there are a lot of similarities in this. And if you wanted to look up more about this, you can watch my JuliaCon talk from 2017. The person in the top left is not me, it's David Sanders. I think I was off screen when I took the screenshot, and I didn't find a good image to put on the slide that had both the title and me in it. So maybe once I've shaved off my hair, this is what I will look like. Coincidentally, Joachim at the same conference gave a talk on SDDP and energy. So if you wanted to learn more about how people around the world solve optimization with hydro and SDDP, you could watch his talk as well. I'm kind of very pleased that members from the New Zealand Electricity Authority are here today, because Auckland has had a long history of modelling optimization under uncertainty for hydro systems. And it goes back to kind of 1991, where one of the founders of Joachim's company came up with this algorithm and started modelling the hydro problem. In 2008, Andy Philpott at the University of Auckland and Zeeman Guang wrote a first model of this for the New Zealand system in AMPL. They later translated it to C++ and wrote this Dowson model. In 2016 or 2015, I started working on the cow problem, and I wrote the first version of the Julia model called SDDP.jl. But I kind of had no interest in the New Zealand energy hydro model. I was just kind of working on my cow thing. And then Leah Kapilovic came along and took the underlying Julia code and wrote the New Zealand hydro model and called it JADE. And then over the last kind of 10 years, we have been improving that JADE model, and now it runs in the Electricity Authority to kind of model the value of water in the New Zealand hydro reservoirs over time. So when we're modeling a sequential decision problem under uncertainty, we need a few elements. First thing we need is a description of this graph, this Markov chain that says how information flows over time between the different boxes. And then for each box, we need 5 things. We need to know what the incoming and outgoing state variables are, those x's. We need to know the control variables. These are the actions that the farmer can take, or whether to turbine water from a hydro lake. We need some constraints, whether they are linear or nonlinear or bounds. We need an objective function that the farmer is trying to maybe minimize their costs each period. And we need some information about that random variable and how that random variable shows up in the objective and the constraints. So this SDDP.jl package is a Julia package for both writing down these sequential decision problems under uncertainty and for solving them. And here's an example of the code for a very simplified hydro model. And we're going to break it down and go through step by step. So the first thing we need is a description of the graph. So here we can say that we're making an SDDP.linear policy graph. So this is going to be a linear graph with 5 stages. So it's the graph in the top right. But there are other types of graphs in the package that you could use as well. So there are kind of Markov chains and cycles and stuff, but the simplest one is this linear graph. We then need to declare our state variables. So here we're making a reservoir that is just one reservoir. And we can say it's got this tag SDDP.state. And then JuMP allows you to extend the macro syntax to do different things. And here, it looks like we're creating one JuMP variable called x reservoir, or x underscore reservoir. But we're actually creating a struct with two decision variables. There's x reservoir.in for that incoming state variable, and x reservoir.out for the outgoing state variable. We can also provide keyword arguments. In this case, this is this initial value that tells us the value of the state variable at the start of time. We need to declare some control variables. These are the actions that people can do. These are just normal JuMP variables. We can say we've got how much thermal energy to burn, and maybe how much energy to make from hydro. We need to define our constraints. So there's a water balance constraint, which effectively says that the amount of water in your reservoir and the outgoing state variable has to be less than or equal to the amount of water in the reservoir in the incoming state variable, less how much I use to make hydroelectricity. And then there's some demand constraint. Maybe it says that the amount of energy made from thermal plus the amount of energy made from hydro has to be equal to 1. You can make this much more complicated, obviously. We need to define the objective for each of those nodes in the graph. In this case, it's just I want to minimize the amount of thermal energy that I'm creating. And this thermal, or this objective, can depend on the stage. So there's a little T up the top that says, hey, you're building a JuMP model for period T. And so the T can appear kind of anywhere in the problem. And then the tricky thing is we need to now define a random variable for the problem. And the random variable for this problem is how much water is going to inflow into the reservoir in each period. And the way we do that is by providing a series of realizations, capital omega. So we can either have 0, 1, or 2 units of water flow into our reservoir. And we need to give a probability vector. So 0 happens with probability 0.3, 1 happens with probability 0.5, and 2 happens with probability 0.2. And then we create a callback in this parameterized function that's going to modify our JuMP model depending on what realization was observed. So it's kind of a little bit terse syntax, but if you go away and kind of think about it, you can probably figure out what's going on. But effectively what we're doing is when we see the realization little omega, we're going to change the right-hand side of that seawater constraint to be the inflow. Inside that parameterization function, you can kind of do anything you like. So you could fix variables, you could change their bounds, you can modify right-hand sides, you can modify coefficients in the problem. Alternatives that we looked at were using maybe like parameter JuMP or parameter opt interface, where we would explicitly declare the parameters. I think longer term, thinking about how we handle parameters in JuMP is an open question. There's kind of multiple ways we could do it and no clear option for what is the best. So putting it all together, we can kind of write down our multi-stage stochastic optimization problem, hopefully in some very kind of nice, terse syntax that's explainable at the same time. And at the bottom, we can go away and train our model and simulate it, but we won't really go into the details of what's exactly going on behind the scenes in the algorithm of how we solve this problem. I just want to give a little hint of it, though. Effectively, we're doing benders, kind of nested benders in multiple chained together. And this involves solving every node in that graph is an LP, say a small JuMP model. And we're going to solve it multiple times, maybe for different realizations of the uncertainty. So we're going to be modifying our subproblems lots of times and resolving. We're going to be adding new constraints, new rows, like we would be doing in Bender's decomposition. And effectively, this is my cow model. In 200 seconds, we solved about 4.5 million LPs. So we're solving lots and lots and lots of LPs. We're modifying things, we're adding new rows, we're updating them, we're resolving. And so JuMP was really useful to be able to write these kind of decomposition algorithms where we're walking over lots of different LPs, modifying them and resolving them. There are a couple of other things I want to talk about how we use JuMP inside the body of the SDDP package. One thing is we have a multi-threading algorithm that turned out to be really easy to use. Each of those nodes in the graph is a separate JuMP model. Each of those nodes has a lock, and effectively we have multiple threads that are walking this graph and solving and modifying problems. And as long as only one thread can access each node at the same time, there's no conflict. And so this worked really well, and it was actually pretty easy to implement. A downside is that Gurobi's environments are currently not thread safe. So we have one jump model for each node in the graph, but Gurobi wanted one license for each thread. And so I kind of need to figure out how to get around this, and this is kind of an open issue. The other issue with multi-threading in Julia is there's kind of very limited tooling to detect race conditions, and so it's kind of like you just cross your fingers and hope you haven't forgotten anything or made a mistake. We also use multiple dispatch to control the algorithm in many places, and perhaps too many places. It's kind of too easy to think, oh, here's a new option that I could add in, and so you end up making a new kind of plugin, and then how they all interact is quite complicated. We can have different risk measures, so how we aggregate the random variables into a single value, how we compute duals when we're doing Bender's decomposition. We need to compute subgradients of our objective functions. There are multiple ways we can do that, especially if there are integers in the problems. There are different ways we can sample the graph. There are different ways we can do the forward pass. There are different ways we can do the backwards pass, and there are kind of others as well. The upside is it's really easy to add new options and kind of change the behavior of the algorithm. The downside is thinking about how they interact gets complicated. So one of the ways that we use this multiple dispatch is for our risk measures. The nice thing is it's like a couple of lines if you come up with a new risk measure. So on the left, you define a new abstract risk measure, in this case for the expectation operator. You need to implement one function or one method in Julia, in this case called adjust probability. It takes in a bunch of arguments that we won't get into. And then when you're training, you can say, I want to train my model using risk measure equals expectation. If you had a different risk measure, in this case the entropic risk measure, you write a separate kind of 5 or 6 line function, and then you say SDDP.train and pass in a different risk measure. And we support many different risk measures. We support CVAR, a lot of distributionally robust ones like Wasserstein. And it's all based on these kind of little plugins that worked really well. And I don't know how we would kind of do this in a different programming language. So multiple dispatch works very well here. We also use multiple dispatch to control how we compute duals of models with integer variables. And we use a couple of JuMP features here, either the relax integrality, so we've solved the problem with integer variables. We just relax all of the integrality, solve the problem as an LP, and then take those duals. Or we can solve the problem as a MIP, fix the integers, then solve the LP with the fixed integers, get those duals, and then use them. Although when we use the fixed discrete duality, there's another step where we have to kind of adjust those duals to make them valid, but we won't go into that. I think there's a few takeaways from this talk. If you're a kind of a modeler, there are many ways to model sequential decisions under uncertainty. They appear in many places. One approach is to model them kind of as I briefly described here, as this graph where time is a Markov chain, and each node we're solving this small decision problem. And then if you have modeled your problem using this SDDP approach, we have a general purpose software that can go and solve that problem and give you back a policy. For other developers of JuMP extensions, the kind of a way you can adjust the macros, like the variable macro, to tag in new types, like the SDDP.state variable, where instead of returning you a single variable, we return you a struct of 2 JuMP variables. It's very nice. It allows you to build really elegant syntax. Turning what was a kind of complicated single-threaded algorithm into a multi-threaded algorithm was really easy, and that gave us a really nice performance win. And then multiple dispatch makes it trivial to kind of adjust your algorithm in various ways via these little plugins. The downside being that then thinking about how those different options combine together often gets quite hard. And that's me.